Okay.
Hello everyone, my name is Tasala Amina and my teammates are Atishe and Giachi. Our project focuses on predicting diseases using deep learning models. We chose this topic because we feel like a model that can complement a doctor's knowledge during the diagnostic process will be beneficial. Previous work only focused on using either only numerical data or just text data to predict diagnosis. And studies have shown that models that handle multiple modalities perform better than unimodal models. In addition, previous studies focused mainly on common diseases. We believe that a model that handles rare diseases will be valuable because for such cases, diagnostic period could be lengthy and ridden with errors, which could have negative impacts on the patient's health condition. For our dataset, we collected data from Mimic3 database, a commonly used dataset used in clinical studies and disease diagnosis. It contains both numeric and text information about patients and their corresponding diagnoses, which are written as ICD-9 codes. After several preprocessing steps, such as removing outliers and missing values, our final dataset contained 10 input features, which are both text and numerical in nature, while the ICD-9 codes were the target prediction for our models. For our methodology, we fed this data into a multimodal network to take advantage of both the numeric and text data for diagnosis predictions. To predict rare diseases, we adopted a one-shot learning strategy using Siemens networks and triplet loss. I'll hand over to Giachi to give more details on the multimodal network.
So details of the multimodal networks is shown in figure 4. So we have an encoder for text and another encoder for numerical values. For the text encoder, provide two options for text encoding. First, using term frequency vector and fully connected layers. And second, we can instead use word-to-vec method based on one-dimensional convolutional layers. We have tried to use all of them in experiments. The result will be presented later. The numerical data encoder is actually normalizing the data to have zero mean and unit variance. Then the latent variables of two encoders will be concatenated and passed into a prediction head with dense layers for the final classification. Also, to avoid severe overfitting, we further add some dropout layers. And then Atisha will introduce more about the one-shot learning.
So one of our aims of our project was to predict rare diseases which have very few samples in the data set, like for example, the mimic data set. So we thought that one-shot learning would be a good fit for that task. The task consists of 172 different diagnoses with 5 samples only each. And the network we are planning to use are called Siamese networks, which is a specific type of one-shot learning. In this Siamese network, as you can see in figure 5, we divide input samples into triplets. So each triplet consists of an anchor sample, a positive sample, and a negative sample. An anchor sample is any input, any sample from the input data set. A positive sample is an input which is of the same class as the anchor sample. And a negative sample is a sample which is of a different class, any other class than the anchor sample. So as you can see in figure 2, we are using something called a triplet loss. So the goal of triplet loss is to separate out negative samples from different class inputs and to bring two samples from the same class closer to each other. Essentially, the final output of the one-shot learning will be an embedding where we basically get clusters of different classes diseases, where each cluster contains samples of the same disease and different clusters are different classes. Now I'll hand it back to Giachi to talk about the results of the multimodal networks.
So in experiments, we first compare the multimodal networks with unimodal networks, which process only text or numerical data. Networks are tested on data with the most frequent 2, 3, 4, 5, or 10 labels. Table 1 shows the average accuracy and standard deviation over 5 tries. Ideally, the multimodal networks should perform better, since it considers data from multiple sources. However, in Table 1, we can see the unimodal network actually works better. This may be due to the overfitting of the complicated multimodal networks. So we tried to tune the dropout rate, add L2 regularization for weights, and use maybe early stop criteria, but they all failed to address the problem. So the problem might lie in the late fusion step. Noticeably, a 2020 CVPR paper had the same finding that the multimodal network has poor performance on some classification tasks. So they proposed a gradient blending algorithm to solve the problem. It looks promising, but we have no time to implement this, so this could be done in future works. And our teacher will introduce some experimental results for the one-shot learning.
So the experiment for rare disease prediction is basically we try to use networks to predict, to classify each input into 172 different classes. So as baselines, we decided to include a simple support vector machine, an SVM model, and a normal two-layer deep learning classifier. Furthermore, since Siamese networks output an embedding and it does not really do classification on its own, we decided to add an SVM at its end for the classification for one model. And for another model, we decided to just look at the closest neighbors and see if it's able to cluster them properly. So the metric we used is accuracy, since it's a classification problem. And we use another metric which is called top 5 accuracy, which means that the ground truth matches any of the 5 most probable cases outputted by the model. This is a common metric used in classification problems where there are a lot of labels, many labels, such as like ours, where there are 170 labels. But as you can see in table 2, the results are opposite to our expectations. The SVM classifier actually performs the best out of all the models, beating out all the deep learning models. And the one-shot learning with the closest neighbor classification actually performed the worst. Furthermore, you could also notice that all of these models, irrespective of which model it is, are overfitting massively, despite using L2 regularization and dropout layers. We are not sure why this is the case, but it is possible that it may be due to the data set, since notes are taken by different doctors from across different hospitals, so there's no really fixed standard for those. So it's possible that our models are not able to generalize the input samples properly. Despite the low performance, one thing to note is that these models are learning something, because as you can see, even the worst accuracy of the one-shot learning, which is 2.6%, is still better than what a random selector would do. So in the future work, we do want to find out whether there's a problem with one-shot learning techniques in general, or whether it's just a Siamese network problem. There are multiple other one-shot learning techniques such as matching networks, prototypical networks, attentive recurrent comparators, and relation networks. And maybe performing experiments on those models will help us understand whether one-shot learning is a good fit for this kind of task, or whether it's not at all. Finally, one important thing we do want to try in the future is to understand why are these models overfitting. Like, irrespective of which model it is, there is some overfitting. And irrespective of any kind of regularization, also there's overfitting. So therefore, understanding why this overfitting is happening would help in fixing it and hopefully improve accuracy of all the models. Thank you.